Now I want to have a look at tracking the controller. I turned one of the controllers on and connected to the base station, and to see how that behaves, and especially I want to have a closer look at drift correction, because there's some interesting thing going on with that is easier to see in the controller. First of all, the controllers are not tracked at the same high frequency as the headset, which, as I mentioned, is at 1006 Hz. The controllers are tracked at 366 Hz, and I again do not know where the last 6 comes from. The primary reason for that, or the primary reasons for that, are that, for one, the tracking the controller is not quite as important as tracking the headset, because if the controller tracking is a little bit janky, it will be annoying, but it won't make you motion sick. And more practically, of course, the headset is connected directly via USB, whereas the controller is connected wirelessly, which I'm assuming is Bluetooth. So I'm guessing that the reduction in tracking rate is primarily due to the limited bandwidth of the wireless connection. But that said, tracking the controller, as you can see here, works very well. Just I want to briefly mention that I have set up the view again, that we are looking directly at my primary Lighthouse base station. So this here would be the Lighthouse's x-axis, this here would be the y-axis, and then this here would be the z-axis of the Lighthouse. So what I want to do is I want to move this thing around really rapidly. I'm just going to swing it around by the cord. You probably shouldn't be doing this, but I'm going to do that now, and then see how it tracks and how drift correction works. So here goes nothing. And now I'm going to collect a bunch of samples. And stop. And now we see the same thing happening that we saw with the headset earlier, that we have these sequences of smooth predicted tracking or dead reckoning tracking. It's not really predicted, it's just based on forward integration of accelerometer and gyroscope data. And then we have these jumps where one or more of the photodiodes on the tracker, on the controller, are hit by a laser, which gives the tracking software a fix on position. But now, if you look at this more closely, we can see something that I think is interesting. And for one, of course, as I mentioned, the tracker doesn't have quite as high an update rate. So between 10 samples on the controller tracker, we are going to have multiple Lighthouse sweeps hitting the controller, because again, that is still 8.3 milliseconds between those. But now 10 of these samples are, oh geez, I'm not doing the math right now. Anyway, if you look at this, you see that, interestingly, the first jump in position is a horizontal jump, and then the next jump is a vertical jump, and the next jump is a horizontal jump, and then a vertical one again, a more or less horizontal one, vertical, horizontal, and so forth. And that I find rather interesting. And of course, once you start thinking about it, it's clear why that is happening. The Lighthouse works by having two lasers that are sweeping out around two rotational axes and sweep out the space. And one of those lasers rotates around the x-axis, and one of the lasers rotates around the Lighthouse's y-axis. But due to the way that the system works, the lasers can't rotate at the same time. So what that means is that one of them sweeps the entire space. Let's say the X laser, the one that rotates around the y-axis, meaning it goes from left to right, it sweeps around, sweeps through the trackable space, and then it goes away, and then the other one sweeps up and down around the x-axis, and then the other Lighthouse comes in. Don't want to go into too much detail there, but what it means is, when the laser that sweeps in x direction from left to right hits the controller, it gives the controller a fix on its x position relative to the Lighthouse, but not on its y position, meaning that the position can only be corrected in x. And then 8.3 milliseconds later, the controller is going to be hit by the vertically sweeping laser that goes in y, and it's going to give it a fix on its y position, but not on x, so it only corrects in y. And then again, 8.33 milliseconds later, it corrects in x and then in y. The reason why these are not as clearly lined up as the others is that these are sweeps from the other base station, which is behind the controller and doesn't use exactly the same coordinate system. And then we have a horizontal fix, vertical fix, horizontal, vertical, and so forth. So what we're seeing here is some of the added engineering difficulty in building the Lighthouse system, unlike with a camera-based tracker, where each camera exposure gives you a full fix on X and Y for each of the tracked LEDs in the Oculus Rift's case. Lighthouse, due to its overlapping, interleaving X and Y scans, gives you an X fix at time t, and then a Y fix at times t plus 8.3 milliseconds, and then an X and a Y, and an X and a Y, and so forth. And still, the system works. That's a very impressive part about this. I just wanted to show this, how well it really works, given this added little wrinkle that I didn't really think about until I started looking at the tracking data. But then, of course, it was rather obvious in hindsight, like most things are.